Hi guys, this lecture presents an overview of YOLO algorithm. Let's look at the topics which we will cover in this lecture. So following are the objectives, or you can say that we have splitted this complete lecture into these 6 parts which are given over here. In the first part, we will see what is YOLO. In the second part, we will see what is basically image classification is. In the third part, we will discuss about object localization. In the fourth part, I will discuss about training of a neural network. In the fifth part, I will discuss why we need YOLO algorithm, why we can't use RCNN, fast RCNN, faster RCNN, mask RCNN. And in the sixth part, we will discuss in detail about the YOLO algorithm and its working. So YOLO is the state-of-the-art object detection algorithm, and it is so fast that it has become a standard way of detecting objects in the field of computer vision. And YOLO is becoming popular day by day. It's gaining popularity. YOLO was invented in 2015, and since then it's 2023 now, and 8 different versions of YOLO has been emerged. So the computer vision community has been continuously working on different YOLO algorithms and producing a better version after every few months. So it can be possible that after few months we can see YOLO V9, and after few months more we can see YOLO V10 as well, because computer vision community has been continuously working on it, and we are getting better and better results. Like with YOLO V8, we are getting a mean average precision of 53.7, which is highest ever in the YOLO history. So YOLO has been continuously gaining popularity, and a lot of work has been done regarding on YOLO. So before YOLO, people were using sliding window object detection. Then more faster versions were invented, which include region-based convolution neural network, fast region-based convolution neural network, faster region-based convolution neural network, and the mask RCNN. But each of these algorithm had its some drawbacks and some key takeaways. We will have a detailed look on RCNN, fast RCNN, and faster RCNN in the next lecture. So from there you will get what are the drawbacks of each of these algorithms. So YOLO was invented in 2015. YOLO outperforms all the other previous object detection algorithms. In image classification, we simply try to classify whether we have the desired object in the image or not. Like in the case over here, we are just trying to classify whether there is a deer or a person in the image. So you can see that, is this a deer or a person in the image? So if we pass this to neural network, or you can say convolution neural network will classify as deer is equal to 1 because we have the deer in the image, and the person will be 0. Or in other case, if we have a person over there, our neural network output will be person is equal to 1 and deer is equal to 0. So in image classification, our goal is to simply classify whether we have the desired object in the image or not. In case of object localization, we are not telling what class basically it is. Is it a deer or a person? But we are also telling about bounding box or the position of object in the image. Where is exactly is the deer inside in the image? So in image classification will simply tell us that there is a deer or some other object in the image. So if there is a deer, it will be 1, or if there is no deer, output will be 0. But in case of object localization, we are not only telling what class it is a deer or some other object, but we are also telling about bounding box or the position of object in the image. Where exactly is the deer in the image, you can say. What exactly is the position of deer in the image? So this is what object localization is. In case of object localization, our output will be in the form of like this. For example, if we have a deer in the image, our neural network will output deer is equal to 1. And if there is no person inside the image, person is equal to 0, because we are doing classification about deer and person. If there is a deer inside the image, or is there a person in the image? So if we have a deer in the image, our neural network output will be deer is equal to 1 and person will be 0. Plus, we have the bounding box around the image, around the detected image. Like you can see, we have detected deer in the image. So we have created a bounding box around the deer. So in place of image classification, we don't have the bounding box. But in case of object localization, we have a bounding box around the detected object, which is deer over here. Neural network, we have an output of this form. For each detected object, we have a vector of size 7, which you can see over here. So here PC represent the probability of class. So if there is some object in the image which we want to detect, for example, if we want to detect a deer or a person, and if the image contain a deer or a person, it means there is an object which we want to detect. So if there exists object which we want to detect, then the probability of class will be 1. The probability of the class will only be 0 if there is no such object in the image which we want to detect. For example, the image is blank. There is no object in the image. So the probability of class is 0. Or there is some other object in the image which we don't want to detect. The probability of class will be 0. If there is any such object inside the image which we want to detect, the probability of class will be 1. The other term is bx and by. Bx and by represents the coordinate for center, which is indicated in the yellow color. So this is the center point of my detected object. So basically bx and by over here represent the coordinates of the center, which is indicated over here in the yellow color, like you can see over here. C1 represent class 1, which is for deer. For example, if we are doing classification of deer and dog, so for a deer or a person, so C1 represents the class 1, which is for deer. C2 represents the class 2, which is for the person. And BW and BH represent the width and height of this red box. Like you can see over here, this red box height and width is being represented by BW and BH. So this is basically BW. And this is basically BH over here. So this is our BH. And PC is equal to 1 if there is an object in any object in the image. If there is no object in the image, PC is equal to 0. And in that case, the rest of the values doesn't matter. So if we have a probability of class 0, then other values don't matter because we don't need these values. Okay, so I hope you got this point. At the training of a neural network. To train a neural network to classify the object as well as the bounding box. So as the neural network only understands numbers, so for each of the image, we will have a corresponding vector of size 7 like this. Like this is the corresponding vector of size 7 for the deer. This is the corresponding vector of size 7 for the person in the image. So in the same way, we can have 10,000s of images. So we need to train a neural network in such a way, if I input a new image, now it will tell us this particular vector in the output. So in this way, we want to train a neural network. Aim is to train a neural network in such a way, if I input a random image at the input, at the output, it will give me a corresponding vector like this. And plus, we will also have an output image with a bounding box around the detected object like this you can see. So this is our aim of a neural network. Like we need to train a neural network in such a way, if I pass some random image at the input, in the output it will give me a vector of size 7 like this, and through using this vector of size 7, I will draw a bounding box around the image, which you can see over here as well. So the question you might all be thinking, that if neural network works so well for object detection, then why do we need YOLO? Because neural networks works well only for a single object. Like you can see here. For example, if we have a deer or a person in the image, like if we have only single object, like there can be a deer or a person in the image. Okay, so if we have a single object in the image, the neural network will give us good results. But if we have multiple objects, like if we have a deer as well as the person in the image, then neural network will not work as good as it did works for a single object. So in case of multiple objects in an image, for example, 5 persons, 1 dog, for example, if we have n number of objects, like 10 objects in the image, then determining the size of neural network is very hard. As I told you, for each object in the image, we have a vector of size 7. Okay, so if we have multiple objects in the image, the vector size increases. Like if we have 10 objects in an image, then the size of vector will be 70. Like we have 70 different vectors of an image. So these become computationally very expensive. So we can draw analysis. If we have a single object in the image, like a deer, person, dog, cat, then neural network works well for object detection. But if we have multiple objects in the image, so if we have 10 objects in the image, then we have 70 vectors. So this becomes computationally very expensive. So we can't use neural network for object detection. Plus, if we have hundreds of objects in the image, then determining of the size of the neural network becomes very hard. So we need to have something that we need to have another approach. So for this, we have YOLO. YOLO algorithm divides the image into grid cells. So for example, here I am using a 4 by 4 grid here. Like you can see over here, we have 4 grids, 1, 2, 3, 4 in horizontal direction, and the 4 number of grids, 1, 2, 3, 4. 4 grids vertically as well. So we can have, this is not necessary that you should have 4 by 4 grid. We can have 19 cross 19 grid, 3 cross 3 grid as well. So if we focus on this specific grid, like this specific grid, so as we have no bounding object in this grid cell, so the probability of the class PC will be 0 and the rest of the values doesn't matter. So as we have no object in this grid cell, so the probability of the class will be 0 and the rest of the values does not matter to us. So now we can see that we have a cow and a girl in the image. We can see that the cow is expanding to 2 grid cells in width, and in terms of height, the cow is expanding to 3 grid cells. So as we can see that the cow is expanding to multiple grid cells, we try to find the central place of the cow, and the cow belongs to that grid cell as shown below. So this is the central place of the cow, and the cow basically belongs to this grid cell. So you can have done the snapshot of this specific grid cell where the central place of the cow is. So here we have a vector for the cow. PC represents the probability of class, which will be 1 as we have a cow in the image. This represents the these represent the center points, and here we have 2 represents the width, as it is covering 2 cells. Like in the width section, it is covering, the cow is covering 2 cells, 1, 2, while in terms of height, the cow is covering 3 cells, 1, 2, 3. Okay, so we have 2, 3 over here. And in the C1 represents the class 1, which is for the cow. So we can have the cow here. So the class will be 1, and this image does not contain the center point of the girl, as it only contains the central point of the cow, central place of the cow. So the C2 represents the class 2, which is for blur, and it will be 0. So as we have divided our image into 4 by 4 grid cells, so total 16 grid cells we have in a single image. Like you can see over here, we have divided our image into 4 cross 4 grid cells, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we have total 16 grid cells in an image. So for each grid cell, we have a vector. So we have 16 such vectors, and each vector length is 7. So we have 16 such vectors of size 7. So for each object, for each grid in the image, like for each of the grid cell in the image, we have a vector like this. So for each image, we'll have 16 such vectors. Like we have 16 such vectors in each image. Similarly, for this image, we will have 16 such vectors of this form in the image. So for each image, we have 16 such vectors, and for the training, we can have thousands of images for the training as well. So in this way, we will train our model. Now in the next slide, we will look at the prediction part. After training our model, if I want to test my model on some sample image, so this is the sample image which I have passed to test my model. So this is the sample image which I have passed to test my model. This is this image. So in the output, I will have 16 such vectors because I have trained my model for 4 by 4 grid cells where each grid cell contains one vector. So we'll have 16 such vectors and the output as well, like you can see here, because our output image will be divided into 4 cross 4 grid cells, and we will have 16 such vectors of this form of the size 7. So each vector size will be 7 in the output. But wait, there can be an issue. The algorithm might detect multiple bounding boxes for each of the object. Like you can see here, for the person, we have two bounding boxes, one with the confidence of 0.45 and other with a confidence of 0.85. For the baby as well, we have two bounding boxes, one with a confidence of 0.75 and other with a confidence of 0.65. And for this, we have two bounding boxes as well, one with a confidence of 0.95 and other with a confidence of 0.35. So if we have multiple bounding boxes for each object, we can't take max for each class. Like for this class, we can't take the max of these two bounding boxes. Like we can't take the 0.95 and remove the other which is less with less confidence score. And we can't take max for this class of baby. Like we can't take the 0.75 bounding box and remove the 0.65 bounding box. And for the person, we can't take the 0.85 bounding box and remove the 0.45 bounding box. So when you face this issue, when you have multiple bounding boxes for each of the detected object, you can't take max, you can't take a bounding box which has the maximum confidence. There should be another way, which is IOU. IOU stands for intersection over union. Let's go into detail in the next slide. To solve the issue of multiple bounding boxes, we use an approach called IOU, which means intersection over union. So if we only take this class person over here, if we only take this class bounding boxes, so you can see we have two bounding boxes for this class person, for only this person. So for class person, we find the overlapping area, and to find the overlapping area, we use intersection over union. If objects are overlapping, the value of intersection over union is more. If they are completely overlapping, the value of intersection over union will be 1. So for example, we can discard all the rectangles which have IOU greater than 0.65 and keep the rectangle which have the class probability as maximum. The same process will be repeated for other classes as well, which means for baby class and for this object class as well. And this is the formula for the IOU, which is intersect area over union area. And in this way, I have explained this process. Like this is our intersection area. You can say the inner area of the blue lines, and this is our union area. This is my union area, and this whole area, this only area is my intersection area. Which we usually use IOU to solve the issue of multiple bounding of boxes. This approach is also named as non-max suppression. So you can also say this approach as non-max suppression. Also, after deducting all objects, we apply non-max suppression and we get the unique bounding boxes in the output. As we have divided our image into 4 by 4 grid cell, so we might sometime face this issue that one grid cell like this has center of two objects. Like this grid cell contain the center of the dog and the girl. So now as this grid cell above can only represent one class, how we can represent two classes? So our one grid cell has a vector. So each grid cell has a vector of size 7 and each grid cell can only represent one single class. We cannot represent two classes in a single vector of size 7. So if we face this issue, how we can solve this issue, let's look in the next slide. So if one grid cell has center of two objects, so in such case, instead of having a single vector of size 7, we can have a vector of size 14. So this first 7 vectors who here, the first 7 numbers over here represent for the first class, and the remaining 7 numbers over here represent for the other class. So if one grid cell has center of two objects, in such case, instead of having a single vector of size 7, we can have a vector of size 40 to solve this issue. So thank you for watching this video tutorial. See you in the next video tutorial. Till then, goodbye.